All right, my friends, well, we are here today to talk about geometric series. So a geometric series is a special kind of series that is in the form, the sum, typically from 0, but could start at anything, to infinity, of a times r to the n power. So just as a heads up, a and r are both constants. And then the n is an exponent. And that's the key. When you recognize you have a geometric series, your n is equal to the exponent. That's how you know you have a geometric series. So what this looks like is if you factor in a, it's like an r to the 0 plus an r to the 1 plus an r squared plus an r cubed and so forth. So that's the form of a geometric series. So some examples of geometric series, we could see, for example, like 3 times 2 to the n power. So that'd be like 3 times 2 to the first, 3 times 2 to the second, plus 3 times 2 to the third, and so forth. Or you could have the sum of 1/4 to the n power. Or sometimes you'll actually see a geometric series written out just in terms of terms. So you might see something like this. So say 3 plus 2 plus 4/3 plus 8/9 plus 16/27 plus. Okay, and the way that you identify that it's a geometric series is you multiply by a constant ratio each time. So you multiply each term by some r, a constant multiplicative ratio, to get the next term. And we can see this on here, right? If we multiply by r, we get to the next term. If you multiply by r, we get to the next term. If you multiply by r, we get to the next term. And you can see that this last one is a geometric series because as I get from one term to the next, I multiply the top by 2 and the bottom by 3. So to get from each term to the next term, I'm multiplying by 2/3. And that's true of every geometric series. To get from one term to the next term, you're just multiplying each term by that r value. Okay, and again, that's just a constant multiplicative ratio. So every time you just multiply by r, and that'll get you the next term in the series. So that's how you know you got a geometric. And again, the r, that's the part that's being raised to the power. All right, now let's go ahead and just jump to the result because this is a pretty powerful one. It's like the p-series. If you just identify a geometric series, you can do these right away. So if you have a series that you know is geometric, so a geometric series that is in the form a times r to the n power, again, where a and r are constants. This converges only if that constant r is smaller than 1 in absolute value, meaning if that r is between -1 and 1. It diverges if that value of r in absolute value is greater than or equal to 1. And that makes sense, right? If you multiply by 2 or by 3 every time, those terms are going to get enormous. If you multiply by a half or a third every time, they're going to get smaller and smaller and smaller, and they're going to get closer to 0. So now, suppose we have something like this. Let's just look at some examples, and I'll just ask, does it converge or diverge? I feel like I slur those words every time I write it. Okay, so let's say we have the series 2/3 to the n. So you should look at this series and say, hey, this is a geometric series. I know it's geometric. I see the n in the exponent. I just have a constant here. Okay, so my r value is 2/3. That r is smaller than 1. So I know it converges. I am done. Great. It's like p-series. If you identify this, it really is a huge time saver, and it's easy to tell if it converges or diverges. Let's look at a couple more. Let's say we have the series of -10 to the nth power over 1,000. Okay, well, let's pull out the constant. So let's write this as 1,000 times -10 to the nth power. So you look at this and say, hey, my r value here is -10. That means the absolute value of my r value is greater than or equal to 1. So looking at this test, if it's greater than or equal to 1, I know my series diverges. My terms just keep getting bigger and bigger. They don't approach 0 even. Let's look at another slightly more complicated one. So let's suppose now we have the series of 3 to the n plus 2 divided by 2 to the n minus 1. Now, you might look at this and get a little confused because you see 2 n's in the exponent. But the tip I want to give you is we're going to use algebra so that we can write this in the form a times r to the n, with some constant times another constant to the n. And the trick we're going to use is if we have 4 to the n over 7 to the n, isn't that the same as just 4/7 to the n power? That's what we're going to do. The other thing is that if we have, 3 to the n plus 1, that's the same as 3 to the n times 3 to the first power. So that's the trick I'm going to use on this. I'm going to rewrite this as the series of 3 to the n times 3 squared over 2 to the n times 2 to the minus 1. Because what I can then do is I can combine these two terms right here. I can turn this into, this is 9 over 2 to the negative 1, so 9 over 2, or 9 over 1/2, or 18, or whatever. But that's the constant times 3/2 to the n power. I'm combining those into a single r that's being raised to the n power. Because now, if we look at this, now I see my r is 3/2. This is a geometric series. That r is bigger than 1, so we know that it diverges. Okay, great. So let me talk, that's geometric series about convergence, divergence, but I want to talk about something cool. If you have a geometric series, you actually can determine what the sum is. And I'm assuming if it converges. Obviously, if it diverges, the sum is infinite. Okay, so here is a cool formula. This is something I promised to show up on the AP test. But if your series converges, meaning that the absolute value of your r is smaller than 1, then if you take that sum of a times r to the n, the formula for that, it's going to sum up to the first term of the series divided by 1 minus r. And again, this is the sum of all infinite terms. So when you add the infinite terms in the series, you will get this formula, the first term of the series divided by 1 minus r. And when I say first term, I literally just mean the first term of the series. So the first term, I just mean plug in the lower bound. And I'll show an example of that. So whatever you start at, if you start at n equals 1, plug in 1. If you start at n equals 5, plug in 5. If you start at 0, plug in 0. So let's, for example, take a look at the sum from 1 to infinity of 1/2 to the n power. Now, if we have to go ahead and actually find this sum, we can, because this is a geometric series. You see that r value was raised to the n exponent. That r value is 1/2. So we know that r is less than 1, so we know it converges. Okay, so that's the r we're going to use in the formula down there. When we want to find the first term of the series, is literally just plug in n equals 1. So at n equals 1, the first term of the series is just 1/2 to the first power, which is, of course, just 1/2. So what that means is the sum is the first term over 1 minus r. So cool. So what that means then is you're going to have the first term is 1/2 over 1 minus 1/2. So you get 1/2 over 1/2. So this beautiful, brilliant series adds up to exactly 1. Cool. So what that's saying is if you take 1/2 and you add a 4th and you add an 8th and then you add a 16th and you keep going infinitely, that sum is going to approach and get infinitely close to 1. Okay, beautiful. Let's take a look at a couple more. So let's take a look, for example, at the sum from 2 to infinity of -3 to the n over 2 to the 2n. Now, what's that? You say a 2n? What's going on there? Well, I want to remind you guys that if you have 2 to the 2n, that's actually equal to 2 squared times n. Because what that means is you multiply the powers, you get back to 2 to the n, which you could also rewrite as 4 to the nth power. Oh, interesting. So what that means is we could rewrite this series, so we want to get it in that nice form. We could rewrite this as the sum from 2 to infinity of -3 to the nth power over 4 to the n, which is the sum of -3 over 4 to the n. So now as you take a look at that, cool. Okay, this is geometric. My r is -3/4. So we know it converges because that r, of course, is less than 1. All right, so if we want to find the first term of the series, the first term, we plug in n equals 2. So when I take n equals 2 and plug it into that series, or that term, so the n equals 2 term is going to be -3/4 squared, which of course is just 9/16. Okay, So that means that my sum is the first term over 1 minus r. So that's 9/16 over 1 minus 3/4. I mean, this is honestly fine. You can leave your answer like this. If you want to be a good boy and clean it up, this is like 9/16. So that's a plus over 7/4. And then you flip that up. So that's like 9 over 16 times 4 over 7. I regret this already. Let's turn that into 1/4. So that's 9/28, which is my birthday. Oh, man, that's cool. Okay, so that's how you can actually find the sum of an infinite series like that. Okay, and then just for an example, if you have a problem that looks like this, like 2 minus 1 plus 1/2 minus 1/4 plus 1/8, and you keep adding forever, that's what we should write this as like a plus ... and you have to find that sum. This is an infinite sum. Well, the key is to recognize it's geometric, right? And you know this is geometric because you multiply by r each time. Right? If you get from term to term, you can see it more easily on the fraction. The top stays the same, you multiply by 1, the bottom multiplies by 2, and then it's negative. The sign keeps flipping. So you're multiplying every time by negative 1/2. We see that at the start, right? 2 times negative 1/2 is negative 1. So you multiply by r, so that r is negative 1/2. And when I say the first term of the series, I literally mean the first term, and if it's written out like that, it's just that one right there, just 2. So that means that my sum is equal to the first term over 1 minus r. So that's just 2 over 1 minus 1/2, also known as 2 over 3/2, and you can flip that up to be 4/3 if you want. Okay, cool. So that's how you use this sum. There's one other type of problem you'll see this in, which is kind of a wacky one. Here's one that was on the AP test a couple years ago. So they told you that you had some sum a sub n, and they told you that it was a geometric series. And they also told you that a sub 0 equals negative 2. And they told you, interestingly, that the third term was equal to positive 1/4. And what they're going to ask you to do is to find r and then find the sum from 0 to infinity of a sub n. Now, I mean, we can do the starting value, right? We know eventually that our sum is going to be the first term over 1 minus r. And we know, of course, that our first term is just right here. We're starting at negative 2 because we're starting at 0. Okay, so it's going to be negative 2 over something. So the question we have to figure out is, what is r? So what is that r value? Okay, and the key on this is that you multiply by r each time. So you can think about it by saying, okay, as I go from a sub 0 to a sub 1 to a sub 2 to a sub 3, every time I multiply by r, right? So if I want to get from a sub 0 to a sub 3, if I multiply a sub 0 times r times r times r, that's going to give me a sub 3. So that's telling me that a sub 0 times r cubed is equal to a sub 3. If I want, and if I wanted to get to r4 or a4, I multiply by r a fourth time. And then what I can do is I could just use these values, right? It's saying I had to multiply by r 3 times to get to this value. So if I take a negative 2 and I multiply by r 3 times, that'll give me a positive 1/4. So that's saying r cubed is negative 1/8. So r is the cube root of negative 1/8, which, like the last problem, is actually negative 1/2. And then you'll plug in your formula. That's 1 minus a minus 1/2. Okay, so that's kind of an interesting term. If you just have a couple terms like that, see if you can find the r that way. All right, and that's geometric series. I know this is a lot, but this is pretty important stuff. And bring me some questions in class, things you're curious about. I'll see you soon.